looking at section 2 of chapter 1. This is displaying quantitative data with graphs. So quantitative data is data that has a quantity to it as opposed to categorical data. So now when we've asked the individual a question, we get back a quantity for an answer, such as how many siblings do you have, or how far is it from your house to the school, or how much money did you make last year. Those are all quantitative values. In this section, we're going to make and interpret dot plots and stem plots of quantitative data, describe the pattern of the distribution and identify outliers, identify the shape of the distribution, make and interpret histograms of quantitative data, and then compare distributions of quantitative data. One of the simplest graphs to construct is a dot plot. Each dot or each data value is shown as a dot, and so we could look at some information like this. Here's the number of goals scored per game by the 2012 U.S. women's soccer team. And so the 2 gets a dot here, and the 1 gets a dot here, and the 5 gets a dot here. That's the only dot here because that's the only game they scored 5 goals. We can see these two numbers out here, 13 and 14, way different than all the other data points. We would call these outliers because they are points that lie out of the pattern. To make a dot plot, we make a horizontal axis or a number line. We label it, put the variable's name down here, put the scale on the axis. You could number in this case by 1s. Sometimes you count by 2s or 3s, but really when you're doing a dot plot, you're going to count by 1s. And then when we want to make a histogram, it's where we're more likely to group these things together. We mark a dot above each location. It's pretty straightforward, just like it sounds right there. When you look at a graph, the whole point of making a graph is because, for example, this list of data is sometimes hard for our brains to really understand. So I make a graph of it because I can grasp what's going on or what the meaning is of these numbers a little bit easier with that visual. So there are 4 things we're really looking for. The book talks about these as your socks, which stands for the shape, the outliers, the center, and the spread. The shape, the outliers, the center, and the spread. Some teachers, I usually talk about cussing the data. So that's the center, unusual observations, shape, and spread, C-U-S-S. But the idea is that we want to look for any sort of patterns. And when I'm looking at the pattern, I talk about the shape of the graph, whether it's, we'll get some ideas in a little bit, but sort of symmetric, skewed to the right or skewed to the left, approximately normal or bell-shaped, sort of uniform. The center, just where do you think the middle is? Where does the middle of this graph seem to be? And how spread out are the numbers? And then, like we said, unusual observations or points that are outliers are values that fall outside of that overall pattern. When you're looking at a graph, be sure you talk about all 4 of these things. Don't forget your socks, or don't forget to cuss the data. Talking about the shape, we could talk about skewness or symmetry. So this, we've got 3 graphs down here. You can see this one here is somewhat symmetric. It's real life data, so it isn't perfectly symmetric. Be conscious not to say that it is symmetric. It's just approximately symmetric. This graph right here looks like it's being pulled out this direction a little bit. If you thought about a symmetric graph and then I yanked on it towards the 70, kind of stretched it out this way, this becomes what we call a left skewed graph. This one here where I've pulled it towards the right is a right skewed graph. A lot of times, things like the number of siblings or when I'm counting something, those frequently end up as a right skewed distribution because I could end up with values way down here, but I'm sort of bounded down on this end. Grades could be left skewed because I'm kind of bounded up here at 100, and then they pull out towards those smaller values, and sometimes we end up with somewhat symmetric graphs. Sometimes we want to compare 2 graphs. So in this case, they've got the household size of houses in South Africa versus houses in the United Kingdom. And these down here would be how many people are living in those particular houses. When it says compare the two, one of the things that commonly comes to my mind is just what's different. But really, when I compare, I want to compare all four things in the SOX or all four things in cussing the data. So when I talk about the center, this graph looks like the center is, oh, I don't know, about 7. Center down here might be about 4. When I talk about unusual observations, we've got somebody with, it looks like 26 people in the house here. That's kind of unusual. But down here, all the data is grouped together. I don't see any unusual observations. The shape of the South African data is very right skewed. It's pulled out towards the right here. This graph here is much less skewed than that, and it's hard for us to really understand this, but this one's much closer to symmetric. And finally, the spread, where in South Africa the households go from 3 to 26, but in the UK it looks like it goes from 2 to 6. So it's much less spread out. Again, when you want to compare data, always discuss all four things: the shape, the center, the spread, and possible outliers. Another graph that we can talk about is a stem plot, sometimes called a stem and leaf plot. This gives us a pretty quick picture of the distribution, but we still have the actual data values on there. So this will make more sense. Let me show you one, and then I'll come back to the rules of how it works. So here's a bunch of data. 20 students were asked, how many pairs of shoes do you have? And these are the responses they gave. And so I could graph these. The stems are the leftmost digit. So this 50 is going to go next to the stem. I'm going to put a 0 right here. We add the leaves in. This 26, that goes right here. This 26, that goes right here. 31, right here. 57, and so on and so forth. After I've added the leaves, I'll go back and reorder the leaves so that the smallest number is closest to the stem. Finally, we'll add a key so that it looks like this down here at the bottom. 4/9 represents a female student who reported having 49 pairs of shoes. So let me go back and show you the rules, and I think it'll make more sense now that you've seen the stem plot. Separate each observation into a stem and a leaf. The leaf is simply the final digit. Write all the possible stems from smallest to largest and draw a vertical line on the right of the column. Write each leaf in the row next to its stem, then rearrange the leaves in increasing order, so the smallest numbers next to the stem. Finally, provide a key that explains in context what these represent. Now notice, if I hadn't had this student, this 49, I would still have a 4 here, so that I keep spacing between, say, the 38 and the 50. So your stems are going to go all the way from the smallest stem to the biggest stem consecutively, not leaving anything out. That's a stem plot or a stem and leaf plot. Now sometimes we end up getting them all bunched together, so we could split the stems. I'll show you one of those. And we can also use back-to-back stem plots for comparative values. So let me show you a back-to-back stem plot. Same question, how many shoes do you have? Now we've got a group of males and a group of females. So we're going to split the stems. Splitting the stems means any student between 0 and 4 pairs of shoes goes here. 5 through 9 goes here. 10 through 14 goes here. 15 through 19 goes here. So I've got like the lower 20s and the upper 20s, the lower 30s and the upper 30s. We put the guys over here on this side. For no particular reason did we put the guys on the right, but we labeled them as such. So we have a guy with 4 pairs of shoes, 3 guys with 5 pairs of shoes, so on and so forth. This does not mean 358 shoes. This means one guy with 35 and another guy with 38. Then we put the females on the left side. Notice again that the small leaves are closest to the stem. So this is 50, another 50, and a 51. And like before, we could compare these things. We could talk about the center of the boys seems to be around, I don't know, 7 shoes maybe. Center of the girls, more like 30. The boys Had a couple boys with 35 and 38 pairs of shoes, which was unusual for boys. The girls pretty evenly spread out. The guys are much more right skewed. Kind of have to turn your head a little bit. Um, Right skewed is also called skewed positively or skewed to the bigger numbers. And sometimes that might be easier for you when you're looking at a stem plot. If you turn your head over towards your left ear, then you can look at this idea and see this is a little more symmetric um, and spread. The guys go from 4 to 38, whereas the girls went from 13 to 57. Key is 4/9 represents a student who had 49 pairs of shoes. Again, a key is a big idea. You don't need to have a key for the girls and the boys. We've labeled them up there, so that's good. Histograms are kind of like dot plots, but we've crammed some of those dots up together. So how to make a histogram? Divide the range of data into classes of equal width. Find how many things fit in there, and then label and scale and title, just like we've done before. Bars can touch now, unlike a bar graph, bars can touch because the number line touches. I'll show you what I mean on an example. This table represents the number of presidents, the number of residents from each state born outside the U.S. So let me explain what that is. There are 20 states who have 5% or less of their population who were born outside of the United States. 13 states have between 5 and 10% of their population foreign born. One state has between 25 and 30 foreign born, and those add up to 50, so that's all the states. So there's no state with more than 30% foreign born residents. We group these together because we're not quite as concerned right now if it was 1.2% or 1.5%. We kind of grouped it together, and we get here that 20 out of the 50 states, 20 states, have between 0 and 5. And notice 5 itself actually goes in this second bar. And we could get a graph. This is called a histogram. We've crammed these bars up next to each other because there are things in every category. If this number right here, this 5, if this had happened to be a 0, we'd still have the space between 10 and 15, but it would just be flat. There wouldn't be a bar there. This is called a histogram. A few mistakes students might make with a histogram. Histograms are different than bar graphs. Remember, bar graphs are for categorical data, so I might say, what type of pet do you have? And so I have a bar for dog and a bar for cat and a bar for fish. With a histogram, I found quantitative data, so I say, hey, state, what percent of your population is foreign born? Don't use counts or percents as data. Okay, so what that means is this means 20 people or 20 states answered something in here. 13 states answered something in here. So I wouldn't want to, for example, take these numbers and add them up. That's not meaningful. Use percents instead of counts on the vertical axis when I have distributions with different number of observations. So if I were to talk about counties and the percentages of counties that were foreign born, I might want to talk about a relative percentage of the counties instead of the raw number of counties, because of course there's more counties in Texas than there are states in the United States. The goal of a graph is not necessarily to make it look nice, it's to have a meaningful display of data. And that doesn't mean we don't want it to be neat, of course. And if it can look nice, that's great, but the point isn't a fancy graph if it doesn't display data meaningfully. So in this section, we learn to make and interpret dot plots and stem plots of quantitative data. We describe the overall pattern of a distribution. identified shapes of distributions. We made and interpret histograms of quantitative data, and we compared distributions of quantitative data.